Yeah. So, hello everyone. So I'm Zhenliang Ma. I'm an associate professor at KTH in the Transport Planning Division. So today I'm going to discuss about this digital twin for urban transportation. So we know that digital twin has been applied successfully mostly in the production industry, but there's also lots of discussion about digital twin for the smart cities in transport, energy, and water. So in this lecture, basically, I will cover some fundamental concept for digital twin, and also take those how we can structure the digital twin for transport. There will be like three product studies that we did in Stockholm. So I will also share some of our work and experience and lessons that we learned from these three products. The first product is about this digital twin for urban traffic emission. Second is like an open source digital twin for public transport. And the last one is actually one of the product we recently received from Swedish Transport Administration on digital twin based network traffic control. So we can start with the definition about the digital twins. There's different definitions if we search for different sources. So here, like in this paper, basically, they define the digital twin as a virtual replica of a physical object or system or process that is used to simulate, analyze, and optimize the real-world counterpart in the real time. So one of the keywords here is basically the real time, right? Probably you also have this confusion about what's the difference between simulation and digital twin, because simulation has been widely used, like in transport, right? This essential tool that we use for planning, management, analysis. The key difference here is that like the simulation is a one-way analysis, right? It's mostly offline. It can be also like do the online simulation, but basically this, let's say the continuous like interaction between the real world data and also the simulation is not there. Right? The digital twins basically it can facilitate this two-way connection between the physical entities and the virtual world. So if you look at this figure, right, this basically we have the physical space in the left. Right, it can be the built environment elements, right, the buildings, traffic light, sensors. It can also be the movement objects, the vehicles. And then we have this information space, what is called like a virtual model, right? We have the abstract representation of the real physical world in order to make the, let's say, optimization and decisions simulations in the virtual environment. So there's interaction between this physical space, basically physical entity provide the data to the information space, and then all the decisions coming from the information space will feed back to the physical world. So digital twin is basically, it's kind of like the bridge between these two worlds. And there's another like concept about the 3D digital twin, 4D digital twin, or 5D digital twin. Right. It's basically like for the digital twin, they start with from the architecture area. It's basically people doing this visualization for the infrastructures, buildings, road, and other things. Right. This is a 3D representation. Is basically people already call this 3D digital twin. And then if we add this fourth dimension, like the infrastructure dynamics or the traffic dynamics or air dynamics, basically this becomes like a 4D digital twin, right? It not only like to realize the static physical objects, but also to simulate the dynamics of those elements in the environment. And for the fifth dimension, if we have a simulation control that we can do the scenario generation and scenario planning or optimization for futures, then we will have another dimension that we can use for decision making. And this will be called 5D digital twin. So this is the definition for those. Basically, like those different dimensions also like shows different information, right? For this 3D dimension is basically where, right? And then the 4D dimension is basically when things happened, how those propagate And the fifth dimension is basically to help us to answer this question: what if we change the land use, or we have new buildings or new infrastructures built in the network? And then if we abstract like those conceptual definitions into some, let's say, architecture, right? What are the key elements for digital twin that we have? And also what are the key functionality they should have in order to be being called a digital twin? So this is like a kind of like abstract of the conceptual model in the previous slide. We have this physical world here, and then we have the sensors and IoT systems for data transmission, data processing. And then in the rightmost, we have this visualization and also the human-computer interaction with the humans. And then in between, basically, we have this key functionality for the digital twin. One is called, we call like a digital replica that can perform this nowcasting and the forecasting functions. Is basically to replicate what is going on, what has happened, and also to predict what will happen. And this digital replica, we can treat this as just like a digital model for the physical world, right? But for decision making, it's different, right? For decision making, we always need to simplify our representation of the physical world. So those type of model is called like a virtual model, right? Virtual model like a mathematical models or simulation models that we are going to use to generate decisions, right? This virtual model will take data from the digital replica module, but basically it is a simpler version depending on different optimization problem or decision making problem. We may have simple digital models in order to make those decisions. And then talking about this architecture, then from the technology perspective, right? What are the main modules that usually a digital twin should have for the platform? So here I just like use this multimodal system, multimodal transport system or mobility system as an example. So we can start from this, the green one, the green box here. We have the physical world. Right? For this, basically we need to have a module we call like a control technology toolbox, right? Different sensors, sensing, communication technologies to be able to facilitate those data collection from the physical system and also the feedback control to this physical world. And then in the bottom, we have this multi-system digital twin, right? So this is like a digital replica of the physical model. So here we have this sensing technology toolbox, and also we need to have this data ingestion platform. It's like the database to try to store, process, and also like probably also to facilitate like efficient queries over the database to combine different sources of the data to facilitate the downstream applications. So M4 is different model libraries, right? As mentioned, we have a 3D, 4D, and 5D. 3D focus on the realization of these physical objects, including the infrastructures, vehicles, pastures, and energy system. But 4D is more like we want to understand the system dynamics. So here, from the mathematical problem, it's called like computing methods, right? It's many inference and prediction models, right? To infer what happened, and based on the experience, we can develop model to predict for the future. For the 5D decision-making models, optimization and simulations are basically the ones that we need. And on the top, M5, basically we have the interface with the users, right? For that, we should facilitate this interface to be easy to accessible and use by the non-technical professionals, right? They can use to understand the problem, to inform what will happen in the system, and also to design for the system for the what-if scenarios. And then across like those different systems, basically we need to have this system management layers. This M6 on the left. This is basically to facilitate this interoperationality and cybersecurity between the data transmission, information transmission among different models. This is basically like a very brief overview about different technological modules that usually need to be built in the digital twin platform. Since like we are in a research field, right? So if we look at the research landscape in this digital twin field, this is one of the review paper from this year. right? You can see like in this, this is like a keyword network visualization. So we have four different colors, right? These red ones, green ones, and also the blue ones, and also this, yeah. For different like colors, basically they have different clusters of the research community. Actually, they work in the digital twin area. Right? If you look at this big node, this digital twin right here, you can see the connected node including circular economy, sustainability, life cycle assessment. Basically, those are the research probably mostly from the planning or from the social science to try to evaluate what's the value of the digital twin to contribute to the sustainability and circular economy in different areas. If you look at these green ones, right, we have this beam, this building information models, infrastructure, facility management, right? So this is probably from the area where the architecture people or the infrastructure management people, they also like build actually the models, the digital twin models, mostly the realization models, in order to realize those physical objects. The blue ones, we have the design, simulation, model system, right? We also do lots of work, probably mostly for this 4D dimension, right? To look at the system dynamics and to try to like do some control management. Then for the red ones, right, we have big data, internet integration, Internet of Things. I would expect like those are mostly from the ECS people, computer science people, and also the sensing technology perspective, how people basically look at that. But there's also some common note in terms of the this what's called the sustainability. I would see I cannot find, but basically there's some common topic basically across different domains, and they are talking about. Um, then when we talk about this platform, right, this is not something that one party or university they can afford the resources to do this, right? So this is like joint work. Maybe we include many different parties or stakeholders to try to develop this. And then in order to facilitate this collaboration, development of this digital twin, there's also like different initiatives, either in the European level, in the country level, they try to develop this standard for the data and AI and data standards, but also the digital twin modeling standards. On the left, basically, this is like one of the popular data standard for the sensing, sensor data communication and transmission things. It's called FIWARE. And the right part is basically the 3D city models, right? 3D city model is mainly focused on the infrastructure realization, but also we need to have this standard, let's say, framework and also language to be used in order to facilitate the collaboration among different cities. The CityJML and CityJSON are two of the popular ones that we use to develop this 3D realization for the buildings, trees, and other things. These standards are very important. Basically, they will ensure the digital twins for different industries, they can talk to each other, right? We have digital twin for transport, to talk to digital twin with energy, right? And to talk with digital twin for waters and other aspect, health, right? In the smart city, right? So we need the standard to be able to talk with each other and also scale across system and also remain future proof. So then now the question is like, okay, those are the general knowledge for the digital twin from different domains. But how we can structure the digital twin for transportation, right? So this is basically the slide I try to show, like how we frame the transportation digital twin, right? What are the functionalities they should have, and also what are the different applications that they can drive. So we talked about this 3D digital twin. So if you look at the physical world on the left, right, in transport theory, we have different sensors, signaling controllers, cameras, and road and buildings. Right? So basically, the first steps that we need to replicate those physical object in this digital twin world, right, on the right. On the right, you see this 3D visualization that actually we developed, which is open source to use. And for this SHISTA area in Stockholm. So this is the first step. It's more like a 3D visualization for these physical objects. Definitely, we need to have some of this interactive realization interfaces so that the planners or the users, they can use that. For the 4D digital twin in transport, basically, as mentioned, we need to have this system dynamics, right? It's basically, we should have built in this situation awareness functionality, right, to inform the current situations. We also need to have this simulation models to predict and forecast for the future traffic flows and things. And all those, like, we output some performance metrics that we can basically monitor and also like to use for decision makings, right? This vehicle energies, emissions, traffic state. For the 5D digital twin, that means we need to have this feedback loop, right? We need to provide for the future scenario decision making, right? This optimal control and management is one of the example here. I put in here that. So basically, this will feedback to the physical world, right? Either to control the flow from the supply side, or they can provide the information to the travelers, right? This information service or personalized information provision. So this is like more like the overall structure about the digital twin for transport that we envision what it should look like, and also what functionality it should have. And the following products, the 3 products that I mentioned, basically they are corresponding to, one is corresponding to this one, 3D digital twin. The other one is basically 4D, and also the recent product that we received is basically to do this 5D, right? This consistent development at KTH. The first product is Gemini, it's digital twin for emission monitoring. It's a collaboration with KTH, MIT, RISE, and also funded by the Sensible Stockholm Lab from the city of Stockholm. The background for this is like, since this is the first project that we work on this digital twin. At that time, our motivation is very simple. It's like we want to find some important topics to look at, and then the main thing is like is to develop this technological digital twin platform. Right? There's not much research actually involved. It's more like we want to like put all the existing technologies, models on one platform to see what we can have. And then the background of the topics that we choose this emission monitoring and the prediction. This is also because of the core focus at that time from the city office. So they have this current state-of-art emission monitoring, which is basically strategic emission maps based on the average yearly traffic flows. They have some equations they can plug in to calculate the emissions for different regions in the country. For this Gemini product, we try to like go more disaggregated way to try to monitor the CO2 emissions in the vehicle level, and also try to predict this vehicle emissions. And if you look at this realization for this, what we try to achieve is that like for each vehicle, we want to quantify what's the source emission from this vehicle when they move on the road. And also we need to also look at the site emissions, right? If I live in this building, what's the emission level for my place, right? So that is like something we try to do. But as I mentioned, like the project focus on the technological development, right? Not like the emission modeling or emission propagation modeling, right? It's basically we have 3 main activities here. One is the platform, right? We need to build this digital twin realization platform that we can showcase on this touchable screens. People can basically explore interactively to look at the emissions in different places. And then there's 2 methods, like I mentioned, this nowcasting and forecasting. We try to build into this platform. So this is the overall framework, right? So there are 2 parts, right? We have the physical world in the left and the digital twin platform on the right. And then you can see there's different box with different shading colors, right? The one that with this blue shaded box are basically the main work that we are going to do. Right. For those, let's say, gray shaded box, basically those are something has been already been developed by RISE. RISE is a research company in Sweden. So basically, they have used the Unity to develop this platform for SHIST already. But what we try to do in this project is that like we want to integrate this simulator to have this forecasting capabilities. And also we want to do this real-time emission monitoring at the vehicle level, use the computer vision techniques. So for the nowcasting part, as mentioned, like the purpose that we want to quantify for the vehicle in real time, what's the emission, what the source emission from these vehicles. And then the data that we have is basically this fixed camera data installed in the intersections. So we have trained some Euro algorithms to try to identify the type of these vehicles. And also we also need to identify the speed of the vehicles in order to use the corpus model, which is the traffic emission model, in order to get these source emission calculations. But basically, this is the part that MIT has been trained. They trained based on the open source data first, and then we have some video footage in the Shista that we collected. We try to fine tune a little bit. Basically, at the end, this like the model can distinguish 7 vehicle classes: the trucks, sedans, or buses, other things. And then at KTH side, we focus on integrate the simulation into this digital twin, right? Basically, the forecasting here we use is the simulation, right? The simulation in transport. Right? If you know like transportation simulation, basically for the regional simulation, which is large scale area simulation, usually MATSIM is good choice. But since the studied area is Kista is a small, let's see, area in the Stockholm city, basically we want to look at the very detailed macroscopic traffic simulation, right? To get the trajectory of the vehicles, then we can also apply this corpus emission model to calculate these vehicle level emissions. So we need to use Sumo. And then the difficulties are how we can combine this regional simulation from MATSIM with this local area traffic, detailed traffic simulation with Sumo to do this, to do the calculation of the emission in the vehicle lab. As I mentioned, the method is there, right? It's not something new, but basically we try to build in those in one platform that we can show everything in one place. In the end, this is basically what RISE has done is to use the Unity platform and also the system realization that we basically integrate everything together in one platform so that we can realize. Yeah, I think if you're interested, probably we can discuss more about this. But this one is basically just like a realization prototype. And then for the left part, actually, there's some of the technological challenges, how to store this real-time streaming data, how to process them, and also how to be queried by this system 3D realization. And also for this system 3D realization, basically, there's also inconsistency between the mapping system, because in the simulation, we probably use a network from, let's say, OpenStreetMap. But on the Unity and the system, probably they use the Google Map as the map system. Basically, this map system inconsistency may cause problem that, yeah, if you cannot align well, basically the vehicles may pass through the buildings or flying on the ground, right? Not like running on the road. There's also like some sensor deployment. Since we also do the emission modeling, we also install some sensors in this Shista area. This picture, left picture, basically shows where the Ericsson parking lot has. So we have some cameras there. We also have some sensors. We try to like look at like how we can calibrate a little bit of this corpus emission model for this local contact. Yeah, this is just like some visualization, the overview about this area in Shista, and then you can see this red part is that like if we transform this Ericsson parking lot to some commercial buildings, right, and then what would be the change of the emissions test. And then there's for the visualization, definitely we can realize the emission in different levels, right? We can aggregate it in the link levels. We can also track each vehicle to the end, right? To get the sense about the emissions when they move. So this is like a quick summary. So basically, in this product, we try to integrate different sensors and computer vision technology to try to do this real-time nowcasting and also simulation for the forecasting of the transport planning. And then we demonstrate in the Shista area. And following that, actually, we have some following work since we have other products not led by KTH, but led by Shista Science City. They are deploying more sensors and cameras to try to, from the sensing perspective, to have like more sensors that we can use for this platform. And then the second future work at that time, actually, we are discussing we need to have this feedback loop. Otherwise, this is just a one-way digital twin, right, from sensors to the visualization. So we are lack of this feedback loop. So that is actually the project 3, the new product that we received. We try to look at this feedback traffic control. So the second product is about this open digital twin for public transport. When we finish the first product, actually, we are thinking because the Unity and also other commercial, let's say, 3D visualization tools, they're expensive, all right? They also like not easily accessible to, let's say, to the transit agencies or like to small companies. Right? And our motivation here is very simple. It's like, how can we like develop some open source digital twin framework that can be used by researchers and by agencies. So this is actually a master thesis project that we try to develop this. As mentioned, this is like the main motivation, right? So we want to develop this open and lightweight digital twin framework. And also we want to open source this code to the public so that everyone can develop digital twin for their city. And then the objective now is full things, right? So basically, this open digital twin should be extendable, right? Extendable in space, in different cities, right? In different years, and it should be open source. All the data input and all the software that we use should be open sourced ones, right? So that we can open for public. And automated, that means when we come to the implementation perspective, right? If we want to transform this digital twin into another city, right? We need to minimize the preparation work for this transformation in a new place. So here, like this is the technological pipeline, right? There's 2 parts. In the bottom, you can see this is 3-dimensional physical object visualization, right? I mentioned like we need to have a visualization platform here on the right. Basically, System is a web-based interactive visualization tool. This is for free. So this is what we choose for the visualization interfaces. And then on the bottom here, you can see we have this CityGML because this system actually can directly to read the CityGML format to realize these buildings, trees, and other things. For different cities, actually, they have maintained the CityGML dataset for different city, like in Stockholm, but it's very old. So here, basically, we develop a different script so that we can start from the OpenStreetMap buildings and information. We can directly transform those to be CityGML format that can be realized in the system, right? It's more like now you will start with the OSM buildings, right? This is like open source also, right? If you have a new city, then you just specify the area that you want to develop your digital twin, and then you get the OpenStreetMap information directly downloaded, and then you will have this 3D visualization of buildings, road, everything in this visualization. On the top is the 4th dimension, right? It's basically for the pub transport, we have a different data set we want to realize. We have a GTFS operation data. We have this OD data, right? And also we can also have a data from the simulation part. So basically this is that like we have different sensors with pub transport services. We also have the data from the simulation. Then we also write script like to transform everything to CZML format CZML is also standard format for 3D visualization in digital twins. Right? So basically, we automate all those transformation, this heavy lifting transformation work. And from the user side, you just need to prepare this open source data set, and then you will get this fancy visualization. So, this is a video from Shesta. So just want to show what it looks like. It's not like so perfect looking, but in transport, obviously, it is good enough for us to analyze things. Right. First, like we can show these 3D buildings. Since OpenStreetMap, they don't have very detailed information of these buildings facade and other things. There's only height and a shape. But basically, yeah, this shows something here. So here we can also like put bus stations, right? And then dynamically, we can show the movement of the cars. You can also see different colors for the links, right? This can be use emissions or energy consumptions to realize these different links. You can choose what attribute you want to use. You can also track these vehicles, the movement from the beginning to the end. I think we also have some buses. Yeah, there's a buses here. So basically, there's also a car in front of the bus. But anyway, like basically you can realize if you have the GTFS data and also have the simulation data for the cars, and then this platform can be easily just plug into use, and then you can realize things in this 3D environment, right? As I mentioned, like to get these vehicles to move on the road, not flying on the sky, also takes lots of time. We also need lots of transformation of the coordination. So, okay, you get a sense what it looks like. Then I think given the time, probably don't have much time to explain detailed use case, right? Because this is also the question where we present our work in the conference. People always ask, okay, why we need digital twin? If we have the simulation, we have the data, we can also like to analyze many things or to optimize things. So we try to like to see what would be the unique benefit of digital twin for different analysis, right? For the nowcasting, basically, we can facilitate this real-time monitoring and control to understand what is going on. Right? And one example here is that, like, okay, if you have the digital twin, basically you can play the historical trajectory of the buses. From the simulation, probably you can also simulate what it should be, right? We have what it is, what has been, but also we think what it should be, right? And then based on that, like we can play back and forth to understand why this bus is delayed, or it's ahead of time, or it's behind the time. This is like a retrospective analysis, right? As mentioned, we know this bus bunching is a very challenging problems in practice. But the question is that like, we have some like models to analyze, what's the other reasons caused this bus bunching. But now, if we have some visualization platform, right, you can interact with it and then to look at like what really happened, right? Because there's so many reasons can contribute this bus function. Is it because this signaling in the intersection is not appropriately set, or is it because there's pedestrians crossing, cause this bus being delayed, or is it because of the congestion, right? But suppose we have all this information in one environment, as a human, we are very good at those visual analytics, right? Yeah, the last one is basically we can automate this planning process, right? Because data twin is not only about the decision making, right? It's a database, right? A database that we can combine different source of data that is related to transport in one place. And then depending on different application, then we can query for different data sets to use, right? The database itself actually has the value for the planning perspective. So the last project is we just recently received. I have not much to see, but probably just share what we plan to do here. Maybe next year, if there's chance, we can present some findings. So this is like a traffic twin, T-twin, digital twin sandbox for network traffic control. The purpose that we want to develop this modular sandbox is more like an environment that we can test different traffic control strategies in this digital twin environment. This is funded by Traffic Market. We also discussed we can also directly connect to the data collection system on the motorways so that we can pilot what would be the control performance for the controllers that we propose compared to what they have already now. The background is basically for this traffic control system in Sweden is very localized. It's called like we have the Swedish version of the traffic control system. It's called Lahora. It's very localized for each intersections separately. So there's no coordination traffic control for most of the network in Sweden. So that is actually the purpose. We try to do is that okay, we can do this network level control to do this proactive. And also like we want to have this digital twin AI technology to be incorporated. In the European level, they have this Acumen product. Actually, they are looking at this digital twin idea for the urban traffic control. And then in the United States, they are actually, the US Department of Energy found this big project of C-Twin to directly pilot this in the real world for this digital twin-based traffic system control. And you saw this picture before, right? For this product, basically, we focus on this yellow shaded part. We want to do this feedback control. Right? We have this realization, we have the simulation being integrated already from these previous two products. And with this product, we try to see how we can do this feedback control. And for the application, basically, we only choose this network traffic flow control application here. And then one thing I would like to share is that like when we talk about this traffic control, right? What would be the difference if we have the digital twin compared against we don't have the digital twin? So on the left, basically this is the real traffic system. TDI system is basically the name for the motorway traffic data collection system in Sweden. And the LASI controllers is basically the hardware that we have that for the signal controls. This is the physical world. Basically, like then we can have this digital twin sandbox, right? Now custom forecasting simulation. And then we have this traffic control optimizers. So in the current practice, it's basically, we don't have the digital twin sandbox. But for the traffic control optimizer, it will be directly connected with this physical world, right? We observe something at the intersection, the traffic flows, delays, things, and then we can use this reinforcement learning to do the signaling plan optimization. And then we will like execute this signal control plan directly to these controllers, the signal controllers. Right? That is current practice. But if we have the digital twin, we can do this differently because we have digital twin as the bridging layers. What we can do is that we can use the reinforcement learning framework that we can have this traffic control optimizer, and then we can generate these candidate actions. But instead of like to execute these candidate actions directly to the physical world, we can test all those candidate actions in the digital twin sandbox. And based on that, basically we can generate lots of experience, right? Given different traffic state, what would be the optimal signal control plans, right? We will store this experience, right? We call like a scenario replay pool, right? And this will like form some like new training data set to try to train our offline trained controllers. If you know about this AI traffic control, we have the offline training, but when we apply in the reality, right, we need to have some continuous learning or transfer learning. But what we need is that we need to have a safe environment to be able to do that. That is like one unique thing that we think that digital twin can reformulate how we can do this control optimization. So after that, we will have this we call like approved control actions that we can execute in the reality. This can make our control to be more safe and robust. And the things that like we need to formulate this new structure, right, is given digital twin, how we can formulate this traffic control problems, and then we can try out in the real world. And then the test site, we chose this Södra Länken, is one of the busy corridors and in Stockholm. Basically, there's lots of closures for this corridor in the peak hours, and there are lots of complaints from the general public. There's certain things that we can do there. This was also a Google product before this. I think Eric is also lead of that product to look at this corridor crowding management. But we want to really look at this place, but we will look at this congestion management from wider area, not only for this specific area for this corridor, but also look at this inner city area, because this is outflow stream, how we can quickly dissipate those flows coming out from the corridors. And also we want to look at the flows from other motorways that have the inflow going through these corridors on the left and also right part. Okay, so I think given the time, basically I would stop here. This is basically the expected result, and we want to develop the T-twin sandbox so that we can test the network level control strategies safely. And then we chose a case study that we in Stockholm to test. This is the last slide, key takeaways, right? It's about the digital twin fundamentals, right? This living digital replica, real time is the keyword, and the three main functionality, nowcasting, forecasting, and decision making. For simulation, I wouldn't say like digital twin simulation or simulation is digital twin. It's more like digital twin will include simulation, right? Simulation is only part of the digital twin. This is the difference. And then three case studies, and also this picture basically is the framework that we think in transport digital twin, how we envision they should look like. Yeah, I will stop here, and thanks very much.